Okay, today I'm going to go through some GCSE questions on waves. I selected a handful for my Year 10 class to do, so it'll also help you if you're doing revision for your GCSE this summer. Okay, so I started off with a few multiple choice questions, which usually come at the beginning of the paper that we do, which is Edexcel International GCSE. So the first question is about this waveform. So it's height against distance. It represents a water wave traveling along the surface of some water. So the first question says, which arrow represents the amplitude? So the answer is S, because the amplitude is the distance from the 0 point or the equilibrium. So the 0 point is the equilibrium or the central position, or the rest position. Okay, so a wave is a disturbance in a medium. So when it stops being disturbed, if this is a water wave, it'll all go back to being flat at 0. So the displacement, or the maximum displacement, is called the amplitude, and the maximum displacement is from the 0 point, so it's S. Which arrow represents the wavelength? Well, the wavelength is the distance between two peaks or two corresponding points. It could be two troughs, or it could be the beginning of a wave to the next wave, which will be Q. Okay? So you're looking for B. And then what type of wave is the water wave? Well, a water wave is a transverse wave. It means it gets displaced up and down as the wave travels this way. So the energy is traveling in one direction and the vibrations are perpendicular, to the direction of the wave travel. Okay, so transverse is when the vibrations are perpendicular to the direction that the wave is going. So if the wave is going this way and the oscillations are up and down, then that's transverse. Remember, longitudinal are drawn by areas of compression, squashed areas, compressed areas, and areas of stretched areas where they are that would be the wavelength. From the center of the squashed area, that would be longitudinal. So this is sound, and water waves and light waves are transverse waves. Over the page, part D. So it's all one question, 3 multiple choice and a 2 marker. The time period is given as 2.7 seconds. Can you calculate the frequency? Well, you need to know that the frequency is 1 over the period. That's a 1. Often my students want to know, what is that, a 1 or an I? Its frequency is the inverse of period, so 1 divided by 2.7 gives you to 2 significant figures. So you should use 2 significant figures, because over here they've given the period to 2 significant figures. 2 significant figures. Your answer should also be to 2 significant figures. That's how you work it out. You get 1 mark for putting the numbers in, 1 mark for the correct answer. Always show you're working in case you do a calculator error, and you could then lose both marks. Question 2 is also from another paper, and it's another multiple choice. So it was a question 1, so they often start with multiple choice or easy to answer questions, quick answers. The question is about waves again. This time it says, which wave is longitudinal? The answer is sound. All electromagnetic waves, which are ultraviolet, radio, infrared, are all EM waves. EM waves, electromagnetic waves, are all transverse. So the only one is sound that's longitudinal, which I drew on the page before. Okay? They then want you to draw a straight line. A straight line means one straight line, linking each of these waves, microwave, infrared, to its correct hazard. Well, infrared is how you can get burnt. Infrared is basically heat. So it basically burns the surface of what it touches. The skin burns, for example. Whereas microwaves can penetrate more deeply, and they use, often with microwave cookers, they use the frequency of water to be able to oscillate water molecules deep inside the material, so it can cause internal heating of tissue. Okay? Depending on the wavelength of the microwave used, it will oscillate different atoms or molecules. Okay? Next question. Which of these is used for X-rays? Which of these is a use for X-rays? I should read, is a use for X-rays? The answer is checking for broken bones. So this is just knowing the uses and dangers of different types of electromagnetic radiation. Again, over the page, the fifth mark this time is which of these is a use for infrared. So remember, infrared is heat, and you use heat to cook food. Okay, so detecting forged banknotes is ultraviolet. Yeah, so if they're forged, you can't see the watermarks in them if you use ultraviolet. If they aren't forged, you'll see that the official notes will have areas which fluoresce under ultraviolet lights. They shine off and give off. You can see other things. Sterilizing medical instruments is usually gamma radiation. I'm sure you could use X-rays as well, but it's normally given as gamma radiation, and we've already done X-rays for bones. Okay, so cooking food is infrared. You could cook food with microwave, but they're asking about infrared. Okay. Personally, I don't use microwaves. I don't like them. I prefer to use traditional methods of cooking. A toy produces continuous waves. So you see the toys in the middle, it's continuous waves, floating on the surface of a pool of water. The waves spread out as circular wavefronts in diagram 1. Diagram 1 shows the wavefront produced when the toy is not moving as viewed from above. So this is viewed from above, and each of these points is called are wavefronts. Okay, so if the toy is not moving but is still vibrating, so it's vibrating, it produces constant vibrations. Therefore, the distance between the wavefronts, you can work out the wavelength from the distance between the circles. Okay. Diagram 2 then shows the wavefronts produced when the toy is moving across the surface of the water. Yeah, you have to draw the arrow to work out, to show the direction the toy is moving in. Well, it's moving in the direction where you can see the center of the circle is moving to the right, and that's causing the wavefronts to become closer in front of the movement because they're kind of catching up with the waves that they produced earlier. Okay, so this is known as the Doppler effect, yeah, which they're going to go on to ask you about. So the waves in front look different to the waves behind, to the observer. Okay, so that's question 5. The first part, the difficult part, so this is another 5 marker, but this time the second part is 4 marks, and it's to explain. Explain means more difficult. Explain how the frequency of the water waves at point A, that means in front of the toy, as I showed you just now, is different to the frequency of the waves at point B, behind the toy. Well, at point A, I'll just show you the waves again. The wavefronts are closer together, yeah, as the toy moves in that direction. The wavefronts being the waves. So the waves in front are closer together, okay? And behind, the waves are further apart, or the wavefronts are further apart. So when the wavefronts are closer, it means they have shorter wavelengths, yeah? So you get 1 mark for explaining they're closer together. That means that technically that means they've got shorter wavelengths. And as the speed of the waves remain constant, because water waves will have a set speed, yes, depending on the conditions of the water, for example, the depth of the water. The only thing that changes the speed of water waves is the depth of the water. So when you, for example, at a seashore, when the waves come into the shallow area, they go slower, so the waves will catch up with the ones in front a little bit. Okay, so since we know that speed is equal to frequency times wavelength, the speed doesn't change, so speed stays the same. If the wavelength gets shorter, that means the frequency must go higher. So if the wavelength is smaller, the frequency must be larger, because frequency and wavelength, you could say, are inversely proportional. Okay, and they multiply to give the same value. So that's how you get the 4 marks, breaking it down and showing you really understand the theory of this is called the Doppler effect. Okay. So that's question 5. The reason that we went from 1, 2, and then 5, as you get, these are the actual GCSE question numbers from the paper I took them with. As they get to higher question numbers, the questions become longer and technically become more difficult. So now this is a difficult question in the exam, and it's multi-parted. Okay, so it has many parts to it. This is a question about refraction. Yeah. State the formula linking critical angle and refractive index. So the critical angle, sine of the critical angle, is equal to 1 over the refractive index of the material. So once you know the refractive index, you can work out the critical angle. In this case, they're talking about diamond, and they've given you the critical angle. They've said C is 26 degrees. So can you now calculate n? They want to see if you can use your scientific calculator properly. Now, if you change the formula around, you'll see that this becomes n equals 1 over sine of 26, which gives you an answer to 3 significant figures of 2.28, and you can round it up to 2 significant figures because here they gave you 2 significant figures. So it's approximately 2.3, and that gives you 2 marks, one for using the equation properly and one for giving the answer correctly. Okay, 2 significant figures is best. Now they've drawn you the diamond that they're talking about. So this is the diamond. The light ray comes in. You notice that it comes in at right angles to the boundary between here is air and here is the diamond. Yes, so this is the diamond pentagonal shape, 5-sided diamond. Because it's going in at right angles or along the normal, it doesn't change direction, but it does still slow down. So the speed will slow down, and the velocity will be actually the speed of light in a vacuum divided by the refractive index. So if you remember, the refractive index was 2.3. So in the diamond, the light will slow down by 2.3 times. But you don't have to know this for this part of the question. It's just so you improve your knowledge. So the ray's coming in. It hits this normal. So they've drawn the normal for you. Remember, all angles are measured to the normal, which is at right angles to the boundary. Angles are not measured to the boundary. So the angle instance here will be 0. Yeah? Now the angle internally is 30 degrees inside the diamond. Now we know the critical angle was 26 degrees from part A. Yeah, A part 1. And we know that 30 degrees is therefore greater than the critical angle. So total internal reflection occurs, and they want you to complete the diagram. Therefore it must reflect at 30 degrees. It then hits this, and because it's not a regular shape, it now hits it at an angle here, where that's the incidence angle this time, which is very small. And then when it comes out in air, it goes back from diamond back into air, it's going to bend away from the normal. Okay, so this is the angle of refraction. It bends away from the normal if it goes from the optically denser material, yeah, into air, which is optically less dense. Okay, so that's how you get 3 marks. 1 for showing it goes there, 1 for showing it's going to bend when it comes to the angle, and 1 to show that it bends away from the normal. So 3 marks for accuracy. Some students only did the first part from what I could see. Okay, that's the first page of question 10, the back and front. It goes on for 2 more pages. So this is why I gave my students a long question, so they need to practice them for when they get into GCSE final year. Student plans an investigation to determine the refractive index of glass. Okay, the student uses a graph of sine I against sine R. So my students actually had plotted this graph of sine I against sine R, but they did it in a virtual lab on the computer very accurately to determine the refractive index. Okay, so we know that the refractive index, Snell's law, is sine I over sine R. Okay, so the point of doing it graphically, they want you to make it into a graph, is that it's the correct method, that you take lots of angles of incidence here and then measure the corresponding angles of refraction, and you plot them or calculate the sine for each one, and then you plot the various sine I's and sine R's that you measure, probably 5 sets of data minimum. Okay, so that's what they want you to talk about. Describe how the student should collect her data. Okay, so you need to know this is a required practical they expect you to know about. You may draw a diagram to support your answer. So this is the diagram you should draw. Yeah, you basically draw the outline of the rectangular block on a piece of paper. Yeah, you then remove it, draw the normal, point all of the angles, all of the rays. So this is a ray going in. Yeah, point all the rays at the point where the normal is crossing the boundary, and then label them. So this would be, for example, your first ray, and then you show where it comes out the other end. You mark it, you take it off, measure the angles, and then you repeat it for a second angle, and you want to get 5 sets of angles of incidence against 5 sets of angle of refraction, and then you need to calculate the sine of each. Okay, so shine a ray. If you said you have to shine a ray ideally at the normal, yeah, 1 mark. Measure the angle, incidence, 1 mark. Measure the angle of refraction corresponding to it, 1 mark. Do it for a range of angles and calculate sine I and sine R. Yeah, that allows you to then plot a graph. Okay, now I've written it in longhand to allow you to stop the video if you want to copy this answer out, which kind of goes through the answers. Okay, so over the page, they've given you their data, and it looks like it's gone a bit fuzzy. It did this yesterday as well, which is rather annoying, the focus level. Anyway, I'm going to go through this again because we're at the end of the video. They're giving you the sine I and sine R values. So you've obviously got this in front of you if you're my students. If not, I'll try and correct it later on if I get a chance. Okay, so they've given you all the sine I's, all the sine R's. You then plot them. Sine I should go on the y-axis and sine R should go on the x-axis. You've got to label both axes, sine I and sine R. If you label them both correctly and you've chosen a suitable scale, I'm going up in 0.1s because that's a suitable scale. Don't go up in funny numbers, yeah, so usually be multiples of 1 or decimals of 1, 2, 5, or those are the numbers you should choose, okay? So it's going up in 0.1s, going across in 0.1s, and then if you're plotting, if you don't plot it accurately, you lose the accuracy mark for plotting. And I did remove the marks if I noticed they hadn't taken care over it. And then once you got that, and the reason you want sine I on that side, you want to find out how much has the y-axis gone up. So I've used the last figure, which is 0.9, yeah, and I've used the last figure for x, 0.56. They want you to use the graph. That means they want you to draw a triangle on the graph, which is from there up all the way, work out how much it goes up against how much it goes across, and divide by one by the other. If you don't do that calculation, you will not get the 2 marks. You have to show that for, oh yes, and 1 mark for the line of best fit, it says here. I'm sorry that my camera went out of focus, but if you found that useful, please like, share, and subscribe if you want to know when other future videos will be produced. Okay, thanks, and hopefully see you in the next video. My students, you need to use my answers to go through the test that I'm going to give back to you and to make improvements using the purple pen method, and that will be part of your homework for the following week.